Bismillahirrahmanirrahim. Assalamu alaikum. Hello everyone. I am Hamza Ziani, PhD student in Julfa University. First of all, I would like to thank the organizers of this conference. So I'm going to present my oral communication titled by Physical Property of Hydrogen Storage, perovskite, calcium, titanium, oxygen, X hydrogen atoms. In topic materials for vulnerable. We start by introduction. Hydrogen storage has become a challenge for researchers of this area because it is cheap, clean, and no pollutant element existing in nature. The current study has been performed in order to calculate the structural, elastic, and electronic properties of perovskite hydrate, calcium, titanium, oxygen, X hydrogen, with X equal 0.368 used for hydrogen storage purposes. Computational details. The properties in this study have been obtained by using the Wayne-Tuka code based on the full potential unit method within DFT. Note that in this method, the wave function is decomposed in spherical harmonic around atomic sizes and in plane waves in the interstitial zone. As for the exchange correlation modeling, the WCGGA has been used for the determination of the structural properties, whereas the MPG-GGA has been utilized for the electronic properties. Results and description. Structural property. Calcium, titanium, oxygen, X hydrogen, X0368 compounds are optimized in the cubic structure with space group PM3M shown in figure 3. The lattice constant A formation energy U and the Y composition of the atom are present in table 1 along with the available literature results. In the position of hydrogen atom at the most stable position are determined by energy minimization for the compound. When the number of hydrogen atoms increases in the structure, the lattice constant increases as expected. The total energy was calculated for this structure, calcium, titanium, 3 oxygen, 6 hydrogen, and was used to determine the ground state properties such as crystal cell volume, lattice constant, and their continuous at the minimum equilibrium volume. Birch-Mormagen equation of state was used for heating the calculated total energy. The formation energy of this compound are displayed in table 1. Regarding the fact that energy deformation is negative, one might conclude that our materials energetically are stable. Elastic properties. The mechanical stability of compounds are determined using 3 independent elastic constants C11, C12, C44 that are the necessary constants of the cubic crystal structure given in table 2. The basic requirement, also called bond stability criteria, to be the mechanically stable compound are as below, like this criteria, relation 2 and 3. In table 2, the calculated CEV values of these materials satisfy all above conditions, which show that just calcium, titanium, oxygen, 6 hydrogen are elastically stable at ambient pressure. These calculated elastic constants have been used to obtain the mechanical properties given in table 2. It can be said that this compound, just calcium, titanium, oxygen, 6 hydrogen, are mechanically stable in this case. In table 3, Poisson ratio is suggested as 0.1 for covalent materials and 0.25 for ionic materials in the literature. The values of Poisson ratio for the steel compound are above 0.25, which indicate that unique character. In addition, G by B ratio used to determine the bonding nature of a material. If G by B ratio is around 1.1, the material has dominantly covalent bonding. If it is around 0.6, the ionic bonding is dominant. Further investigation are carried out by examining the ratio of bulk modulus to shear modulus by G. This ratio is an indication of the material's ductility or brittleness. Accordingly, if B by G is higher than 1.75, the material is ductile, otherwise it is brittle. Beside on this criteria and the obtained values given in table 3, it is seen that calcium titanium 3 oxygen 6 hydrogen are ductile. For hydrogen storage applications, the ductile materials are preferable because they do not need any requirement. Calcium titanium 3 oxygen 6 hydrogen atoms is a preferable material for hydrogen storage application. The gravimetric hydrogen density is a key parameter for solid state hydrogen storage. For calcium titanium 3 oxygen 6 hydrogen atoms is calculated using the equation below. The gravimetric of calcium titanium 3 oxygen 6 hydrogen atoms is found to be 4.26%. Another important parameter that needs to be checked for hydrogen storage is that hydrogen dissolution temperature. The calculated dissolution temperature for calcium titanium 3 oxygen 6 hydrogen are found to be equal 828.24. Electronic properties. The band stacked for calcium titanium 3 oxygen 6 hydrogen atom cubic mass has been calculated along the high symmetry point in the first boson shown in figure 3. Calcium titanium 3 oxygen 6 hydrogen is cubic mass has indirect band gap which is 1.0 electron volt. Moreover, total and partial density of state obtained from the band structure is given figure 3. Conclusion: the properties of these aqueous compounds are studied, and it has been found that calcium titanium 3 oxygen 3 hydrogen and calcium titanium 3 oxygen 8 hydrogen are unstable compounds. The mechanical stability investigation of the energetically stable compound revealed that only calcium titanium 3 oxygen 6 hydrogen compound are energetically and mechanically stable compounds. The gravimetric hydrogen storage capacity of calcium titanium 3 oxygen 6 hydrogen atoms is calculated as 4.26%, and the hydrogen dissolution temperature is determined as 828.2 Kelvin. These properties are important for hydrogen storage application. The information derived from this study might be useful for hydrogen storage purposes. Thank you very much.